We don't have to concern ourselves, well, yeah. For a tree fern like this, it's a fairly smooth surface. But for this bird of paradise flower, you see these epicuticular waxes are stringy, like, threads or something on the surface. The presence of these waxes increases the leaf boundary layer because the air around all these waxes is not moving much, if at all. Whereas the air closer to this surface, you have to get a lot closer to this surface to reach the still air than you do for this surface. So the nature of the leaf surface affects the boundary layer. And that's due in part to epicuticular waxes or any hairs or trichomes in the surface. It's also affected by the nature of the cuticle. So here is a thick waxy cuticle from this plant, Rhipsalis dissimilis. And here's the surface view of the stomatal openings. And if you look at a cross section, the stomata are down here, and this cuticle is very thick and waxy, and there's a tunnel right through it to where the stomatal opening is. In this plant, Coletia also has the guard cells removed from the free air, but this plant makes like tubes coming out from each stomatal pair, each guard cell pair. And so that also increases this layer of still air next to the surface. And these kinds of arrangements are common for plants adapted to xeric environments, for really dry environments, because it reduces the rate of water loss, because it increases the boundary layer resistance, or decreases the boundary layer component. If you're a water vapor molecule, you've got to diffuse through a longer pathway than if this was open to the atmosphere. So the boundary layer, here's a diagram that sort of shows what I'm talking about. If this is a solid surface, and we've got some air moving over this solid surface, this is an engineering diagram, so it says wall, but let's consider this to be the leaf surface. And we've got an airstream moving over that leaf surface. What the boundary layer is a layer of air next to the surface whose characteristics are distorted by the presence of that surface. So in this case, we're looking at the wind speed, the velocity above the surface. And right at the surface, it's zero. Right next to the surface, the air is not moving at all. Those molecules are in position. But if you get, the farther and farther away you get from the surface, the faster the air is moving, until you get to a point at which it doesn't matter if the surface is there or not. That is the boundary layer thickness. This thickness that you have to, the distance you have to get away from the surface to remove the influence of the surface on the wind speed. So it depends if you have a rough surface, a smooth surface. It also depends on how fast the wind is blowing. So for a fast wind, the boundary layer thickness is small. For slow moving air, the boundary layer thickness is big. And so here's a empirical formula for the stomatal, or for the boundary layer resistance in seconds per meter in velocity units. This comes from a person who was a meteorologist. Okay, so the boundary layer resistance, empirically, 180 times L over V to the half power, square root of L over V. L is the leaf length in the direction that the wind is blowing, and V is the wind speed. So the higher the wind speed, the smaller the resistance, the smaller the boundary layer resistance. The lower the wind speed, the higher the resistance. the bigger the leaf, the higher the resistance, the boundary layer resistance. The smaller the leaf, the lower the boundary layer resistance. That's with wind. With no wind, you see another one there. So empirically, this equation, and the reason I spent time on it, is the important characteristics for determining the boundary layer resistance are the dimensions of the leaf, which the plant has some control over, right, when it's growing the leaf. But more importantly, the wind speed, which is always changing. So the boundary layer resistance is always changing. And the plant has to adapt to that in order to balance these priorities of losing water vapor, or losing water and gaining carbon. Here's another picture of a leaf surface with some trichomes, right? These things sticking out of the surface of the leaf, which increase the thickness of that still air next to the leaf, increase the boundary layer resistance. And you can see the stomatal pores. Moving right along. So far, I've tried to talk mostly about the diffusion of water vapor away from the leaf. But on the other hand, there's CO2 moving towards the leaf. It's a diffusive process, and especially the movement through the stomatal pore. That's purely diffusive. So it's a movement of a species driven by its concentration gradient. High concentration or low concentration. High concentration of water vapor inside the leaf, low concentration in the atmosphere, the water molecules move out. They diffuse out. And in the stomatal pore, that's a purely diffusive process. Diffusion, as you remember, depends on the size of the thing that's diffusing and the medium through which it's diffusing. And so if we're talking about water vapor, and we have a stomatal resistance or stomatal conductance for water vapor, at the same stomatal dimensions and same stomatal opening, the stomatal resistance or conductance for CO2 will be a different number. That's because CO2 is a bigger molecule than water vapor, and so it diffuses slower than water vapor does through a given pathway. We can convert between stomatal conductance for water vapor and stomatal conductance for CO2 by using this factor of 1.6. So that's the ratio of the diffusivities of CO2 and water vapor and air. 1.6. So the stomatal conductance for CO2 is 1.6 times smaller than the stomatal conductance for water, because it's a bigger molecule and diffuses slower. That's fine for the stomatal part of the pathway. But in the boundary layer part of the pathway, it's a quasi-diffusive process. It's diffuse, it's mostly diffusive, but there's some turbulent transport in that boundary layer. And so you can go through an engineering analysis that I won't bore you with here, and convince yourself that the right factor to use is 1.6 to the 2/3 power, which turns out to be 1.37. Right? So a bit different factor. And so if we're computing the total leaf conductance for water vapor, we get one value. But if we compute the same, for the same conditions and the same wind speed, same stomatal opening, we'd have a different number for the total leaf conductance for CO2. And so if we're using a simple equation where the net photosynthetic rate is the total leaf conductance for CO2 times Ca minus Ci. Yeah, like that for now. And compare that with the transpiration equation where we've got this. These total conductances are different values for the same conditions because diffusion plays a big role in the transport in and out of those walls. Okay. And these are useful equations. These are useful. Well, here, I'll change this to E like I have one here. These are useful equations to consider. But they're first approximations, as you can tell. And it's important then to distinguish whether we're talking about CO2 or water vapor in quantifying stomatal conductance and total and boundary. All right, here's a table from Park-Nobel's book about representative conductances and resistances for plant leaf. So let's just take a look at this column in the middle, which has the molar units. For water vapor diffusing out of leaves, boundary layer, a thick boundary layer may have a boundary layer conductance of 3,000 millimoles per square meter per second, 3 moles per square meter per second. That's a thin boundary layer, a high wind speed. A thick boundary layer, 0.3 moles per square meter per second. And I already told you that stomatal conductances are in the order of 1 mole per square meter per second. And so you can see that the boundary layer is similar order of magnitude, and so it can't be ignored. Stomatal conductance, he's got a value of 1.3. That's a high stomatal conductance. Low value 0.07 moles per square meter per second, and you see some variations. Cuticular conductance, instead of 3 or 1.3, 0.004 or 0.016. So orders of magnitude smaller. That's why usually we can ignore the cuticular conductance when we want to quantify the total leaf conductance. Okay, so you can continue this analysis by thinking of, all right, well, inside the leaf, the water vapor is coming from evaporation from the cell walls, from water in the cell walls, into the intercellular airspace. And so there's a resistance or a conductance associated with diffusion through that airspace inside the leaf before you even get to the stomata. And here are estimates of that intercellular airspace conductance. This is for water vapor. This is for water vapor. For CO2, if you're thinking, you've got the boundary layer, you've got the stomatal conductance, you've got that intercellular airspace conductance. Then the CO2 dissolves into the water in the cell wall, has to move across the membrane to where the chloroplast is, across that chloroplast membrane into the stroma of the chloroplast, and dissolve in, be dissolved in that fluid until it gets to where Rubisco is, where the action takes place, and that CO2 is fixed with our EVP. So there's an additional set of resistances or conductances in that pathway for CO2 moving in. And with CO2, that series of hindrances to CO2 moving in, namely the intercellular airspace, the dissolving in the water in the cell wall, moving into the cell, into the chloroplast, is collectively called the mesophyll resistance. And there are ways that people have characterized that. For example, this, as I said, the simple equation for net CO2 assimilation rate total leaf conductance for CO2, Ca minus Ci. Ca is the ambient CO2 concentration, like in this room. Ci is the CO2 concentration in the intercellular air spaces in the leaf. But that's not quite right, because that's not where photosynthesis takes place. It's in the chloroplast. So there's an additional component that's not included in this term that people have become focused on and tried to quantify, and how that varies. And it is quite variable, but that's a topic for another day. So here's a conversion between molar units and velocity units, if you're interested in changing those. These are all those listed here. As I said, this is Park Nobel's book, Physical, Chemical, and Environmental Science. Right? Simple, right? Here's the Halloween picture there with this. All right. Guard cell metabolism. How do these things work? That's what. And well, okay. So this is a confocal image of a pair of guard cells, and these red blobs are chloroplasts. So guard cells have chloroplasts. They do photosynthesis, believe it or not. Guard cell metabolism. All right. Well, as I said, the unique features of guard cells. A unique feature of guard cells is their enhanced ability to osmoregulate, to change their concentration of solutes. And here's a table from a chapter called Guard Cell Bioenergetics from a book called Stomatal Function, you can find in the library if you're interested. And it shows the changes in concentration of some important solutes. Arguably, well, in addition to sucrose that we'll get to later, potassium, chloride, and malate. Potassium chloride, malate, and sucrose are the four most important solutes in guard cell, whose concentration changes dramatically if the stoma is open versus if it's closed. So here are some, let's go through this a little bit. Potassium concentration. Okay, so the content, the amount per guard cell for an open stomata is about 2 picomoles per guard cell. Right, pico is 10 to the minus whatever it is. Something small, right? What is it, 12, I think? No, 10 to the minus 12. Micro. Anyway, whatever it is, small amount. When the guard cells are closed,